Dr. Debu is currently served as a CTO of Ambient Scientific for an always-on AI processor company. He's a very well-known expert in AI machine learning algorithm and architecture. And have very deep knowledge of training and inference and the development of algorithm for machine learning architecture, silicon, and system. So let's welcome Dr. Debu to give the talk on on-device, always-on AI, challenges and opportunities. Please take it away. Thank you.
Thank you. Let me share my screen and then I'll put on the presentation.
Yeah, I think you need to go to the, yeah, okay.
Yes, just a second. All right, so this is the title slides. So you already know what I'm talking about. On device, always on AI challenges and opportunities. We are an always on AI processor company, so that's my talk is about that. As we all know, AI is the most important thing of this century. AI workload requires a lot of compute resources and performance, but traditionally computers were not, and even today probably are not designed for AI workload, and hence they are not efficient. So it requires many of the computers along with necessary cooling and power delivery, which has kept AI compute stuck in data centers. In this workshop, there has been many discussions about business applications, opportunities, and what can be done in data center and what kind of networks can be run. And I'm sure there'll be more presentations on that. But what I am going to take you down is along the lines of the fact that AI compute is moving out of data center, going to the edge, and going to the extreme edge. So along those lines, let me go to my next slide. So as you all know, and I'm sure you have been listening even in this conference, that AI compute is moving to the edge. And it's moving to the edge because of the reasons of privacy, connectivity, and latency, which is requiring localized compute for AI. And also that is bringing in new requirements for energy efficiency, etc. But, you know, AI is very powerful. It can, if we deal with it properly, it can become an extension of our own intelligence and sensory mechanism. And you will see what I mean by that. If we enable this properly, then it can save and enrich our lives by being everywhere, every day, every moment with us. So AI can perform critical functions. It can also perform non-critical functions. It can also aid and enrich our life in the form of entertainment and amusement. So intelligence actually is moving to the extreme edge to always on battery operated devices where no internet connection is required. So that's what I'm going to focus on, and the applications and what those are and how that can save lives, do important things, critical things, and other things that enrich our life. So with that, I'm going to move to the next slide. So let's talk about very critical, severe problems in the world. So AI for everyday lives. So the first thing that I wanted to bring up is women and child abuse, violence event detection and warning. So what, you know, I will be shocked. I am shocked to actually see that 1 in 4 girls are sexually abused before the age of 18. 1 in 13 boys are sexually abused. The statistics says that the sexual abuse of women worldwide is 35%, which means more than 5 billion cases in just 10 years. Here are some horrific pictures. It shocks us when we see these. There was an incident, and I don't want to name the person, but there was an incident where a college student was gang raped in front of her companion in a moving bus in 2012. This horrible incident lasted for 2 hours. The student and her companions had mobile phones, but they were so stunned that they couldn't use it. The attackers took it away and destroyed them right away. And the college student later on died, despite all efforts by the family and government. Imagine a tiny device hidden somewhere in person's body that could detect the signals of distress and send the information to the family or police. In that case, the horrendous event could be stopped. AI has the power to stop abuse or violence. More importantly, the power to deter these. One of Ambient Scientific's missions is to develop AI solutions to stop these types of heinous crimes. This is probably something that we don't want, nobody wants, and there is no solution today. Only probably AI, which is portable, battery operated, always on, with the right detection, could alert or prevent or deter such things. Other examples for the AI for everyday lives. Disaster detection and alerts. For example, there is a car accident and someone in the automobile is stuck and can't reach the phone. He screams, but dies within the car because the doors are jammed. There's no one to attend. Imagine a small device that the driver screams for help and the device listens and acts, informs loved one, police, emergency, etc. So AI can solve this and make things happen. And one of our mission, again, is to help people through AI in such distress. Again, this needs to be always on, battery powered, small, and have to work without internet connections. Because you cannot guarantee 24/7 connectivity, etc. Another example is elderly or child monitoring. So we all have parents, they're elderly. I have known a friend of mine whose dad had, another friend's mother had fallen and passed away because nobody was there to attend to it. But AI can certainly detect if somebody is falling and alert somebody and probably prevent, in most cases, the sad event that has happened in my friend's case. Same thing with a child trying to, in this case, trying to plug in to a wall socket and might get an electric shock or electrocuted. So what can AI do for us to prevent or deter these? Well, maybe a small device can recognize such stressful situations and act. AI can actually solve these things and make things happen. And again, one of Ambient's mission is to help people in these stressful situations. Now, these are events where lives will be saved. I'm talking about that kind of event. But of course, there are other things that an always-on AI will do. But these still are important things. These still will save lives. For example, fire hazard, fire and smoke and sparks. This is a hazard. You can actually have a small unit that can be put. It's not necessarily only at home, but could be industrial. All over the place, battery operated, without internet connection, detects the hazard and sends an alert and saves the place from burning down. Today, we use smoke detectors, but smoke detectors take much longer to detect, and depending on the height and where the smoke detector is placed, it can take minutes before it actually starts detecting the smoke. By that time, damage might have been done. But if you put an AI-enabled sensor all over the place, which is battery operated and small, it will detect it immediately, and in a matter of probably a second or less than a second, it will send an alert. So maybe it will prevent the disaster or deter it. This is an example of trains running on the same track. And this is a real example case where we actually were asked, can there be a small device with always-on AI that can be used to listen to, but by just listening to the sound of the two trains being on the same track, it is different from trains being in different tracks. And if that can be detected, then an accident like this could be prevented. This is another example. This is not like the sexual abuse or violence or somebody dying by falling, but these are probably more rare events that happens, but still these are important problems to be solved. Again, small gadgets, AI can help avoid these disasters. These devices will be with us as a part of our ambience. I mean, so that means we'll put it all over the place, like the fire and smoke in the train. It will be distributed, it will be put all over the place so that they can listen, they can see, and they can alert. Moving on to the lighter note, AI can also enrich our lives. For example, we can talk to a voice remote, or we can talk directly to the appliances at home and say, TV on, fan on, computer on, TV off, turn off dish, turn on my dishwasher, for the washer dryer, this is stained clothes, stuff like that. So it's voice commands, but this is something that enriches our life. This is not a life and death situation. This is not something where we have horrendous outcomes, but this certainly, makes our life better. Moving on, this is another example where it can enrich our lives. So human presence detection. Two key use cases. Detect someone approaching the computer and turn on the screen before the user touches the laptop. And then when the user walks away from the laptop, puts the laptop to sleep. Then there could be added privacy. Lock up the laptop when it detects no presence of human, no presence of the user. There could be another privacy issue. For example, if somebody is using the computer and there is an onlooker looking into, unwanted onlooker, looking into the screen, if it detects that, it could shut down the screen. So there are these applications where one could ask, why would you need an always-on AI for a laptop? Well, the reason is that when you want to turn off the screen, they don't want to use the main processor to do these things. They want something that is always on, consumes the least energy, and turns things on and off without actually using the processor. There could be other things that could happen, and this will lead to sensor fusion, for example. There are people who are sensitive to privacy, so they may not want a camera. They might want to use a radar or a time of flight kind of a sensor. So in that case, there will be sensor fusion between vision, between radar, between time of flight, etc. Now, summarizing, there are already existing on-device AI applications and markets. And what are these? Always on voice, always on vision, always on sensor fusion. And I've tried to give a few examples of these. And these are use cases for which there are needs and there are products that are being built. and always on AI will be part of these. Actually, enabling these life enriching applications are also a part of Ambient's mission. Now, I have talked about different scenarios, different applications, life-saving applications, life enriching applications, etc. Now, what I'm going to talk about is the fact that we do all these things, but we also have to make money. So obviously, we are going to focus on these products that are on this slide on the lighter note before we can go solve the bigger problems that I talked about in the beginning. So what are the challenges? AI requires performance. We all know that AI compute is very challenging. AI workload requires very high performance. High performance and the portability / battery operated devices, they don't go together. And also, moreover, high performance can be expensive. So what do we do? Well, we somehow need to figure out how we can get both power efficiency and cost efficiency while we maintain high performance. And this is a challenge. Now, what happens next? Well, what are the challenges for an always-on, on-device AI? What is on-device AI? What are the challenges and what is always-on and what is all these things are about? First question is, could we build a device that sleeps most of the time and wakes up only when somebody triggers it? As I mentioned to you, AI is all around us. It has to be always on for the applications, for the cases that I have been talking about. It's always monitoring, watching, listening, sensing, and these things need to run AI inference on the device, not on the cloud. AI inference needs to happen without internet connectivity. It needs to be battery powered, runs without recharging for long times, runs for months, preferably for years, without replacing or recharging. So how do we go about solving these problems? Of course, we have to innovate. Innovation shows the way. And challenges are nothing new to us. When presented with the prospect of darkness, we invented light. We have always overcome challenges through inventions. Inventions are our nature. This is in the nature of the human being. Inventions are on our path. Next, I'll explain to you how Ambient is making always-on AI possible for our everyday lives. So this is for those classes of applications that I have been talking about, those classes of devices that I'm talking about, where it's always on device, without internet. How are we making that happen? Well, so let's talk about the challenges and some more. So next few slides will focus on exposing you to the technical challenges and possible solutions. So let's go one by one. AI processing must be extremely energy efficient for these devices and these applications. Conventional digital accelerators don't have a prayer. Well, you all know about memory wall, and I'll reiterate that. Accelerator approach for always on-device AI is not the right solution. For data center AI or edge servers, often it's the right solution, the accelerator, but it's not sufficient for always on AI. We need a system level solution. An energy efficient AI accelerator is only a part of the overall value proposition. A typical system level solution includes several other external parts. If you look at a solution for a board that does battery operated AI, it actually has to bring in signals from sensors. Often these are analog signals, so it has an ADC in case of an analog sensor input. It has a host, external host. It has a signal processing pipeline for pre and post processing, often done in an external DSP. It has a PLL, which is power hungry, and more. So external components actually are power hungry and they're high BOM cost. So what's the right solution? Because this, you can't have a solution where it's power hungry, high cost for these applications. They have to be extremely energy efficient and extremely low cost. So what is the right solution? An integrated ultra low power, small footprint SoC, because all these things have to be integrated. They have to be designed, not only just the accelerator, but also the other things have to be designed so that they are small footprint and ultra low power. And those things have to be all integrated inside your SoC. So all system level components must be designed for the lowest power and cost. They must meet performance requirement for the processing, must be most energy efficient, small footprint AI core, and everything has to be integrated. So this is a huge challenge. This is a huge challenge to do this. So opportunities for innovation. So obviously there are lots of opportunities. These are challenges, but it brings us opportunities to innovate. So let's talk about that. Let's talk about the memory wall first. I think, I think I'm maybe preaching to the choir, but we all know that if memory is separated from the processor, then fundamentally it raises the communication cost. And I'm showing in this diagram the cost of bringing data from the memory into the processor for different size memories up to DRAM. And you can see the processing cost, the actual compute cost is much lower than the cost of bringing data from the memory. So more data, bigger array, larger communication distance, more communications energy. So energy, if you can eliminate, so the first question sort of shows that if you can eliminate the data movement, you can save a lot of energy. So why not do that? So well, memory wall consumes 80% energy in moving data in and out of the memory. So making compute more energy efficient does not really help if we don't solve that problem. So we need an entirely different approach. So in-memory computing is one way to proceed. Why? Because it eliminates communications cost, number one. Okay, what are the other things that we can do? Well, other opportunities for innovation. If you look at the AI compute, 80% of all operations are matrix multiplication or something that can be converted into matrix multiplication. So if we can design an ultra low power in-memory compute matrix multiplication engine, that will be tremendously helpful. Communication cost is eliminated. Also, going from digital, if we can change the way we do the compute, hybrid digital plus analog, compute cost will be further reduced. So the power will be reduced. I mean, this diagram actually shows that 80% that I'm talking about in the matrix multiplication kind of operation, and everything else is the rest. So single few word operands, traditional, and these are all near memory computation. So it's not just only the in-memory computer, but also it requires other things. So in-memory compute must integrate in a programmable heterogeneous architecture. So that needs to happen. So let me now talk about what we are doing about IMC, the in-memory compute. So what we have developed is an in-memory matrix computer that actually can do a matrix multiplication in one cycle. And this is a logical view. This is not definitely how the circuit internally looks like. This is one monolithic block, but it does compute a whole matrix computation in one cycle and uses analog mixed signal techniques. Actually, it's we call it DGAN because it's a hybrid. And it does reduce the power tremendously. And it's very compact, very, very small. It's custom designed, very small, very ultra low power. And we call this a 3D computer because if you look at the matrix multiplication, it's a cubic computation. So we call it a 3D computer or a cubic computer. So just to show a glimpse of that, it kind of looks like this. Again, conceptually. So if you look at it, operands keep coming. We have loaded the memory with the weights and the computation happens. The neurons get computed and results come out. And the structure is such that you can compute, depending on the size of the matrix, a whole matrix or part of the matrix all at once. And again, this is a very, very low power and very small form factor because everything is custom designed. Now, the IMC matrix computer integrates into the heterogeneous architecture. So this is sort of a block diagram of one of our cores. So here is the input buffer. Here is the matrix computer. Output neurons come out, goes into a SIMD computer for doing other things. Then there are activation circuits, and of course there are crossbars. So crossbars are there in between SIMD and the activation circuits so that you can move data around between different neurons, etc. And then the lower crossbar is there to move data around between cores. And of course, we have designed our own RISC processor to sequence through all of these so that we can actually do the computation for the layer, etc. What we have developed is an always-on on-device AI processor. So this you are looking at our chip. So this is a full SoC. It has 5 of those cores in the bottom part and 5 in the top part. There's an ARM processor, and I'll explain what that's doing. And then there is this sensor DMA, etc. So what does the bottom part do? That has integrated all the signal processing pipeline, ADCs, clocks, if you need FFTs, whatsoever is needed, video processing pipeline, it's all custom design integrated for low power. And then that feeds into, the output of that feeds into the AI engine. And this is always on. It's always listening, always watching. And then when it detects a wake word or a trigger or an event or an anomaly, it wakes up. If needed, it wakes up the rest of the AI cores, wakes up the ARM, etc. What is ARM doing? ARM is basically a control processor that configures the chip, and it can run on RTOS, it can run applications, but it doesn't do AI processing. And all of those components that I talked about, we don't need any external components. So we save a lot of power. And because it's custom design is very small form factors, the cost is low. So, but it's highly programmable because we have developed our own ISA. You can actually program any neural network. There is no limitation, small or large. If it is small, it will all fit on the chip. If it is if it is larger, then it will still fit on the chip because we have on-chip storage, on-chip cache. If it is much larger, then of course, just like anybody else, we have to go outside and grab it from external memory as we need. But for most of the always-on applications, that doesn't seem to be the case. It can be run all on chip usually. And this is, again, a challenge. I'll talk about that. So this complete SoC actually enables battery-powered AI, and it can replace the MCUs and MPUs that are being used today for these applications, and they're much more power efficient than those MCUs and MPUs who are currently being used, as opposed to, there are some targeted accelerators for certain types of applications, but not for general applications. Moving on, I would like to compare results based on what we can achieve with in-memory compute versus what you see in the industry today. And I'm going to compare against wake-word detection. So today, the solutions largely available are MCU based, and they consume 10 milliwatt or more. There are solutions that are accelerator based. While the accelerator consumes low power, and that's what gets advertised, but they need all these other things that I talked about. So overall power becomes in the range of 3 milliwatts. Now, what does ambient solution cost? Because we've integrated everything, we can do the same application at 80 microwatt. And so we can be running and running and running for a very, very long time. True battery operated, always on AI. So let me talk about some of the other challenges, areas of innovation, research topics, etc. So neural network models for always-on applications need to be compact. Preferably fits in the in-memory computing blocks for lowest power consumption. What's the next best option? Fit the models in on-chip storage so that it can be paged. Going outside the chip to flash or DRAM consumes too much power. Next is types of model and impact on accuracy. What types of models are best suited for always-on application? What types of models? Because there are all kinds of models. So this is an area to be explored and understood. Like for this type of application, what's best? What kind of models are best? You can have, for example, you can do wake-word detection using CNN. You can do wake-word detection using LSTMs or GRUs, or GRUs with dense, LSTM with dense. So what's the best? What gives you the smallest sized models while not compromising the accuracy? What do you need for voice commands? What do you need for fire and smoke detection? It doesn't have to be high. These are not high throughput applications necessarily, but these have to be accurate. So the question is, how small can the models be without material loss of accuracy? But this, if you look at item number 1 versus item number 2, these are actually pulling you in different opposite directions, because you don't want to lose accuracy. So typically, not to lose accuracy, you end up with larger models, more weights, etc., more layers, whatever. But if you want it to fit in the memory on chip or in IMC, it needs to be smaller. So it's a sort of opposing requirement. Next question is, can sparsity be exploited in memory computing to increase energy efficiency and or increase throughput if needed? That's the question. There are trade-offs. For example, size of the in-memory computing memory, number of cores, size of chip storage. These are all trade-offs that will determine, how large of a model can you put there. How much power is that going to consume if you have to do paging from the storage on the chip, how you move things between cores, how much of a memory should there be in-memory computing, so that you don't have to go to the cache, if you will, which is still on the chip and not page. And then, of course, you one has to worry about the impact on battery life. So, for example, if you have to run larger networks, so let's say there is a trigger, there's a wake word that wakes up the chip. So, and then starts running a larger network because the application requires that. But typically, the always-on part keeps consuming power all the time. But this event will happen infrequently. It will come up, it will do the job, it will go back to sleep. So the question is, when this kind of stuff happens, what's the impact on battery life? Because it is easy to calculate the impact on battery life for the always-on block, but these are infrequent events, but they still amount to having impact on battery life and how large of a model, etc., and what applications. So there are more things to think about, and there are more innovation and research to be done. But I have just listed these 5 for now. So with that, I'm going to open it up to Q&A.
Thank you, Deb, for the talk. It was really enlightening, and it's really interesting to see the advancements we have made for the edge computing. Any questions from the audience? Until we wait for more questions, I can just ask a few. So I was quite excited to see that the energy footprint is really low, because as we know, it edge devices, especially when they have to be always on and use a AI chip, it consumes a lot of energy. And one of the issues when it comes to wearable devices is that we cannot charge it quite often, or people forget to charge it.
Just to give an example, we have customers who, so for example, voice remotes. They want to, these voice remotes never get charged. You put the battery and then you forget about it until you replace the battery, right? And they want to talk to the voice remote and give commands. TV on, TV off, channel this, turn on CNN, etc. There are lots of these commands. So no recharging even. And it needs to last for months.
That's interesting to know, actually. Months is a huge advancement.
Yeah, because that's what people expect these batteries to last for months for a remote control, like for a TV or something, right, at home.
Yeah. So do you attribute this advancement to integrating analog and digital, like the trademark chip that you have?
So there are different pieces. One is the analog digital computing, analog digital hybrid computing. As a part of the in-memory computing structure. So we eliminate the data movement and as much as possible. And then we reduce the power consumption by doing more efficient, energy efficient calculation. But on top of that, see, these things are not just an AI accelerator, as I was pointing out. So what happens, for example, when you talk to these, you are talking, and then there is a microphone. It could be an analog microphone, it could be a digital microphone. Analog microphone typically is lower power, but you have to then digitize that using an A to D converter. Typically, an accelerator won't have those, so it will be external. And this A to D converter will consume power, and there are interfaces, because signal being transmitted from an external A to D converter into the chip consumes power. And then there are clocks and PLLs. If they are external, they consume power. There is a host controller that consumes power. In our case, and then there is signal processing pipeline, like if you have to do filtering, if you have to do an FFT, because often, depending on what kind of network you run, if you run certain types of network, you actually do FFT, then you do mail conversion, then you extract features, then you feed it into a neural network. So if you don't have all those kinds of pipeline or ability to do those calculations, like we do, we can do all kinds of DSP calculations, even from starting from 4-bit all the way to 32-bit inside the engine. So we can do all those things, but most people can't. They have designed point accelerators or accelerators that's not used for DSP computations or DSP pipelines. Then you have to do those outside. So if you add all those things and then put your accelerator, then the power goes up. So that was the diagram that I showed in the middle, where they're consuming close to 3 milliwatt. Whereas by doing custom designing these things and integrating all of these things along with the accelerator, we achieve the power consumption that's needed. So you can't only have the accelerator. That's, of course, the most important thing, but all the other things matter because it's a system solution.
Yeah, that's a holistic approach. Good, definitely like to see more. Being said that, what more areas would you encourage? Like you gave a lot of new areas that people can do research in. So yes. What are the new advancements you would like to see in this field? Like you said, one is the holistic approach, another is having a mixed dish LAN log signal chip. With respect to processing over, like communicating it with the central AI system, do you see a chance of advancements there that we have a more capable NN where the small AI chip then communicates to the main central compute?
Typically these are not supposed to communicate with anybody except for sending alerts, because communication takes energy, right? For example, if you have Wi-Fi, that's going to consume more energy than the chip consumes, for example. Right? So you can, so the idea is not to, if you have to communicate something, for example, fire and smoke, it needs to send the alert, but that's just like a byte saying fire, no fire, right? It sends when there's a fire, when there's a smoke. There are different bytes it's sending, but sends it and then stops, right? So you have that kind of communication, but if you, when you're talking about communicate with the central computer, yeah, there will be a command and control system, which, yeah, of course, like if people go put these things all over the place, which is what they are intending to do, this fire and smoke thing, they intend to put these sensors all over the place because these are not expensive. You don't, today, what do they have? They have smoke detectors. If they don't need want smoke detectors, they have to buy actually cameras, which have to be connected either using Wi-Fi or using Ethernet, connected to a server. And these units will have probably, most likely, will have a NVIDIA Jetson processor or something like that. And it's going to be very costly and it's going to be power hungry. It is going to be an infrastructure build-up situation. Here you just go plop it, and then they just come talk to your command and control center, depending on what happens, and they are there for a long time, right? So it's very different approach.
Yeah, that I think that makes it interesting. Well, thank you for your talk. I encourage audience to put their questions in the text box, and I think you'd be gracious enough to reply. So thank you for your talk again.